In this video, we are going to discuss chapter 6 from your textbook, the 2 raised to k factorial designs. So let's first try to understand the unique features of the 2 raised to k factorial designs. So k means number of factors. Any experiment in which there are k factors and each factor is at 2 levels, those experiments are called 2 raised to k factorial designs. So the base represents the level of factors and the exponent k represents the number of factors. So what's so unique about this is every factor has only two levels, a low level and a high level, which we can call. So this is a special case in because every factor has uh, only two levels. So this is a special case of general factorial design, k factors all at two levels. The two levels are usually called as low and high. These factors can be quantitative as well as qualitative. But even though the factors can be quantitative, we still uh, called the two levels as low and high. This type of experimental designs are very widely used in industrial experimentation, and they form a basic building block for other very useful experimental designs. Also, there are special shortcut methods for analysis of this type of designs. So, what we will do is we will take an example and we will try to understand the 2 raised to k factorial designs through that example. So, I have a simple example here of a chemical process. Let me read the problem statement. Then we have the data for the experiment from the experiment, and then we will perform the analysis. So, as an example, consider an investigation into the effect of concentration of the reactant and the amount of catalyst on the conversion yield in a chemical process. So, your response variable is the yield of the process, and higher the yield, better it is, right? And there are two factors that may affect the yield. One of the factor is concentration of the reactant, and other factor is the amount of catalyst. The objective of the experiment was to determine if adjustments to either of these two factors would increase the response value variable, which is yield. Let the reactant concentration be factor A, let's call it factor A, and the catalyst, let's call it factor B. Now factor A has two levels and factor B has two levels. So this is, if you say 2 raised to k, and in our case k is equal to two factors. So this is the simplest case we are looking at, 2 raised to two factors, 2 raised to 2 factorial design, right? That's the simplest case. We start with k is equal to 2, the least value of k. So the catalyst is factor B, uh, with the high level denoting. First, let's talk about the factor A levels. Factor A has two levels, uh, low level and high level. So, what is low level in this case? Let's say 15% reactant concentration we call is one level, that is we call it low, and 25% reactant concentration is a high level of factor A. And for factor B, which is catalyst, we have two levels again, the high level denoting the use of 2 pounds of catalyst in the chemical process, and low level denoting the use of only 1 pound of uh, catalyst in the process. The experiment is replicated three times. So at each combination, each unique combination of factor A and factor B, three experiments were performed. And how many unique combinations do we have between factor A and factor B? Well, 2 raised to 2. So 2 raised to 2 is equal to 4. So there are four unique experiments. One is at, for example, low level of A and low level of B. Another one, low level of A, high level of B. Then high level of A, low level of B, and high level of A and high level of B. So four unique experiments we can perform. and we are going to replicate the experiment three times at each combination. So there are total 4 times 3, 12 experiments, 12 runs. The order in which these experiments were performed, uh, they were randomly performed, right? Randomization is one of the basic principles of design of experiments. So this is a completely randomized experiment. So here is the data collected for the experiment. So we indicate low level by minus and high level by plus. So factor A and factor B, low low, high low, low high, and high high. That's the treatment combination, right? And at each combination we have three experiments performed, and these are the values of the yield: 28, 25, 27. So we have total of 12 experiments, 12 runs, and we collected the values of the yield for each experiment. Factor A, as we know, is the reactant concentration, and factor B is catalyst amount, and our response variable Y is recovery yield. So let's put this data in a graphical format. So here is how the simplest case 2 raised to 2 looks like on a graph. On x-axis, we plotted reactant concentration, and on y-axis, amount of catalyst. So you can see for A there is a 15% reactant concentration is low value, and 25% reactant concentration high value. And on y-axis, 1 pound of catalyst low value and 2 pounds of catalyst high value. So minus, plus, minus B and plus B. Sometimes people use minus 1 plus 1 instead of just using minus and plus. Uh, and we have these four corner points indicating four treatment combinations. And these three replicates, if we add them, we get the total 80. Three replicates at this combination, uh, we add them totally 60, and so on and so forth. Now you will see the labels. There are special labels that are used. So how this label work? So whichever, uh, in any combination of factor labels, whichever is high, or maybe both of them are high, right? The factor that is at the high level is indicated by the lowercase letter for that factor. So for example, uh, factor which is at high level, lowercase letter is used to indicate that. And if the factor is at low level, no letter is used. So at this combination, here in this corner, factor A is at high level, so we use lowercase letter high, and factor B as B is at low level, so there is no letter for B. So when you see small cap, so that label, small case A, indicates factor A high, factor B low. Here both factors are at high, so A, B. At this combination only factor B is high, so we'll use lowercase letter B. Factor A is at low level, so we're not going to use any letter there, right? And here, since both factors are at low level, we use 1 in parenthesis as a label, to indicate all the factors are at low level. Okay, so that is that. And these bullet points, we already explained that. For example, minus and plus denote the low and high level of a factor respectively, and low and high are arbitrary terms. Like for example, if we have a qualitative factor, uh, there's no, low doesn't mean actually low, right? uh, there are arbitrary terms that are used. Geometrically, the four runs form the corner of the square. Here factors can be quantitative or qualitative, uh, although their treatment in the final model will be different. So in this case, our both our factors are quantitative, because we can vary the reactant concentration between 15% to 20%. This is also quantity, amount of catalyst. So both of our factors are quantitative. So that's basically the graphical representation of the problem. Now, to perform the analysis of variance in 2 raised to k factorial designs, here is the procedure. First, we estimate the factor effects. Then we formulate the model, statistical model that we need to use. Uh, with replication, if we are using, we are performing more than one experiment at each combination. If our sample size is more than one, then you can use full factorial model. With an unreplicated design, there we have, if we have only sample size of one, then uh, the problem with that is we won't be able to capture experimental error. So in that case, there are some special techniques that we will learn, not in this video, but in future video. This video will exclusively focus on this problem here. So with an unreplicated design, one of the technique is you can use normal probability plots. So we'll go over that. We'll use a problem to explain that. Then we perform the statistical testing ANOVA, and then based on your ANOVA results, some terms in your model may be significant, some terms may be insignificant. So then what you can do is you can remove the terms that are insignificant and refine your model. Next thing you can do is analyze the residuals to make sure that the assumptions underlying your statistical model, they are valid. So like we have done residual analysis in the past, such as we do the normality plot for residuals. Uh, we also check the constant variance assumption, and finally we interpret the results. So in our problem here, we want to estimate the factor effects, right? Estimate the factor effects. How do we do that? What will be the effect of A? What is the effect of A on uh, the yield, on the response variable? So that effect can be calculated using, say, if you take this is the high A and this is low A. So six experiments shown here are at factor A is at high level, and factor these six experiments here is factor A at low level. So if you take average of these values, six values, and subtract the average of these six values from them, then that will give you the effect of factor A. Similarly, for effect of factor B, this is high B. So you take the average of these four and subtract average of the this sorry as this average of these six, and subtract the average of these six from that to get the effect of factor B. So that's what is represented mathematically here. Effect of factor A is y bar average of those six readings at A plus minus y bar sub A minus low level of A, and that y bar A plus is AB plus A divided by 2n. So AB plus A, the sum of these values, right, divided by 2n. Any sample size is 3, and 2 times 3 is 6 experiments. So that is that. And then similarly on the low side, B plus 1 divided by 2n. Now if you take 1 over 2n common and write the numerator in the parenthesis as AB plus A minus B minus 1 in parenthesis. So this is called as contrast for factor A. Okay, this is a special term, contrast for factor A, and if we divide it by 2n, we get the uh, effect of factor A. Then for factor B, we have y bar B plus minus y bar B minus uh, average of six readings at high B minus average of six readings at low B. And there we have that AB plus B divided by 2n minus A plus 1 in that label 1 in parenthesis divided by 2n. Once again, you take the 2n out, and what you see in here in a square bracket is the contrast of B. Now, what about the interaction effect? For interaction effect, you take the average of this diagonal 6 readings and subtract the average of these diagonal 6 readings. So you will see AB plus 1 divided by 2n minus A plus B divided by 2n. So here, same formula. That's the formula that I was talking about. Okay, so then take 2n out of the uh, parenthesis, and you have this is called as the contrast of interaction effect AB. Uh, so we will calculate that, and then after that we can uh, calculate the sum squares, uh, and we can uh, do the analysis of variance. So let's do this analysis right from here in Excel. I have already, let's see, I have already uh, entered the data in Excel. So this is what I got. Let's see if can make a full screen. Okay, so here we are. Now we have factor A and B, their labels minus and plus, low and high, and we have replicate values. So one thing we can do is we can add these totals here, total. So sum of these three observations, okay, and then we can just scroll them down. And if you want to put label for each treatment combination, just to make it easy, label those four labels at the four corners of the square. We can do that. So here both factors are at low levels, so we are not going to use any lowercase letter, right? We're going to use one in parenthesis. But I guess before that we have to format these cells as text cells. So right click, format cells, and format them as text. Okay, so here we have the label one in parenthesis there. Here we have factor A is at high level and factor B is at low level. So lowercase letter for A and nothing for B. Here factor B is at high level and factor A is at low level. So lowercase letter for factor B and nothing for A. Here both factors are at high level. So we can say AB. Okay, so we got that. Now let's create the ANOVA table. We'll also combine the initial factor estimation in ANOVA table itself. ANOVA table. Um, First, let's write down source of variation. Source of variation. Basically, the factor, interaction, error, and total. So those are factor A, okay, factor A, factor B, and if you don't want to make them bold, that's fine too. AB interaction effect. So this is a reactant concentration, factor A. Factor B is the catalyst. This is the interaction effect term. Then we have experimental error and the total variation. So total variation and how it is divided in these four things: A, factor B, interaction effect AB, and error term. Next, we can calculate the contrast. Okay, then the factor effects, and those we get from we are going to use these formulas to calculate the contrast, and we divide by 2n. That's factor effect. That then next is let's see, sum squares, right? Sum of squares. Then we will calculate degrees of freedom. Next we will calculate mean squares, then the f value and related p value. And I guess we can wrap the text, center it, make it bold across the. Okay, so contrast, this is the contrast, ab plus a minus b minus 1. So basically contrast is equal to, we need to add high a's here, uh, high side, high side minus the low side, and then divide by 2n. So let's add high side, right? So we have the total of three replicates for uh, each row already. Now we need to look at high a, which is this is high a, right? So we're gonna take this total plus another high a is this last row, so plus this minus, we have to subtract low a values from this, right? So this is low a, I'm going to select that, plus low a is this, so high a minus low a, that's the contrast. And the total of all these six observations minus total of these six observations, and then so we got the contrast, and then we are going to divide by 2n to get the effect. But before that, let's calculate the contrast for factor b and ab. So factor b is high b minus low b, just like that. So equal, let's add high b values. So these two looks like high b, so this plus this minus, we have to subtract the sum of these two values from that, because these are the two low b values. So this plus this value, so that's minus 30. And for interaction, we gonna do these diagonal values and subtract these diagonal values from that. So let's work on that. So we are going to add the lower left corner is this in the on our square, plus higher right corner plus plus, uh, sorry, I should be selecting the value actually, plus high, right, minus the other corner, which is this plus this, so 100 plus 60. So that's the factor effect of interaction effect, the contrast for the interaction. Now we need to divide these values by 2n to find to do the initial estimation of factor effects. So let's do that. Let's divide this value by 2n. So 2 times n is the sample size, which is 3 replicates, 3 experiments performed at the same combination. So that is that gives us 8.33, and then we can just drag it. So there we have it, and I think our answer, uh, let's see if it matches with answer here. 8.33, yes, so we're looking good here. So let's look at these effects. So factor A seems to have the highest effect on the process yield, right? The more the it's a positive effect, high positive effect. So more the reactant concentration, more the yield looks like. Factor B, which is the amount of catalyst, looks like the second significant effect, uh, and negative effect. So at lower amount of catalyst, you are getting better yield, and higher, if you use higher amounts of catalyst, basically you are getting lower yield. Interaction effect is not as significant as the main effects of factor A and B, right? It's very little, 1.66. So that is that. Now, how to calculate sum of squares? So sum of squares is uh, basically contrast square and divided by 4n. Here, to calculate effect, we divided contrast by 2n. To calculate sum of squares, you take contrast square and divide it by 4n. So let's do that. Equal to contrast square divided by 4n. So 4 times 3 replicates 4n, and uh, that is the value you got us. Then you can drag it for factor B, interaction effect A, B, sum square error. To calculate that, first we will have to calculate sum square total, the total variation, right? So, and then we can, once we have that, we can subtract these three from that to get the sum square error. So how to calculate sum square total? So the formula is basically summation of all individual yij squares, summation of all individual yij squares minus the summation, the square of the summation of all these observations, which is basically y dot 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 will be the total of these observations, right? Y dot dot dot, and we square that, y dot 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 square divided by 4n. So let me do it here so you'll understand better. So first let's square these terms. Okay, so I'm gonna let me make it full screen. Okay, let me square these terms. So I'm gonna use square of that, and then all 12 observations we have to square them. So I'm just gonna drag them sideways and then down. So here we have all the 12 observations and their squares, right? So these are individual yijk, where I indicate the factor A, uh, J indicates the factor B level, and K indicates the sample size number. First sample, second sample, third sample. So this is if minus minus is 1 1, or this would be basically y, well, y I j k. I means low level of factor A, so y, let's say 1, y1 b, low level of factor b1, y1 1, and first sample size, so y1 1 1. This should be y1 1 2, this should be y1 1 3, then and so on and so forth. And then we have this yijk squares. So uh, and then we are going to sum of all individual yij squares. So sum of all these minus sum of the square of the sum of the all 12 observations. So let's write down that it is basically let's first sum all these observations, right? That is y dot dot dot, and take the square of that. So I'm going to put this in parentheses and square it. So summation of all yij squares minus y dot 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 square here, and that one, the second term is should be divided by 4n. So 4 times number of experiments 3. So that gives you your sum squares, total sum of squares. Okay, we have some mistake here. Let's see in the formula. Okay, let's see where the mistake is. It looks like there is an extra. Okay, I think that's good. Okay, so the total sum of squares is 323, and now to calculate sum square error, you can uh, add these three and subtract them from 323. So I say 323 minus summation of these three, and that's your sum of squares for error. Now let me put it to up to two decimal places. So I'm going to format sales number two decimal places. So that looks good. Now let's talk about degrees of freedom for factor A. So we have two levels of factor A, minus and plus. So two levels of factor A, that means the degrees of freedom is 2 minus 1, which is 1. We have two levels of factor B as well. That means degrees of freedom for B would be 2 minus 1 is 1. Then the degrees of freedom for the interaction effect is basically the multiplication of degrees of freedom for factor A times degrees of freedom for factor B. So that is 1 times 1 is 1 again. Then for error, let's first calculate the total, and then we can subtract these three from the total to get the degrees of freedom for error. So total is basically, since we performed a total of 12 experiments, 12 minus 1, which would be 11. So 11 total degrees of freedom. And for error then is equal to 11 minus summation of these three, basically 11 minus 3, and that's going to be 8. So that's how you get the degrees of freedom. Now to calculate mean squares, you divide sum squares by degrees of freedom. You should all know this by now because we have done analysis of, we have extensively used analysis of variance in previous chapters for different statistical models. So this is nothing new. So sum of squares divided by degrees of freedom. So that is mean square for A, mean square B, mean square for the interaction effect, and mean square error. Okay. Now let's calculate F value for, because we want to statistically prove whether the initial estimation that we did uh, it's a statistically significant effect of a on the output on the yield is statistically significant or not. Same goes for b and interaction. So once we calculate f value, we can compare that with f critical value at alpha significance level of 0.05 or 5%. uh, or we can calculate the associated p value and compare it with alpha. So let's calculate f first. So f value for factor a is uh, mean square a divided by mean square error. That's always the case, right? uh, we want to see the variation caused by factor a. We want to compare that with respect to the standard experimental error. If variation caused by factor a is significantly higher than the standard experimental error, that means factor a has to be significant. Its effect on the yield has to be significant. And that's why we compare mean square of factor a with mean square of error. And that's why the formula is numerator we have mean square, and denominator we have mean square for factor a, denominator we have mean square error. So that will give us how many times the mean square of factor a is uh, as compared to factor mean square for error. So that is that. So that's a very significant f value 53. So it's going to be highly significant, it's like no doubt. uh, for factor b, similarly you take mean square for factor b divided by mean square error. Once again, 19 is also very significantly high value. For interaction effect, you take the mean square interaction divided by mean square error. So those are the f values for our main effects as well as interaction effect. And now, based on those f values, let's calculate the probability distribution in the tail of this right tail of this f uh, distribution, right? So let's there is a function in excel that we can use. So let me go to the formulas. We need a statistical group of functions, so more functions, statistical. And here the function that I'm looking for is f dist rt. If you scroll your mouse, it tells you returns the right tailed f probability distribution. So that's what we want. So we select that. Our x value is basically our f value, and our degrees of freedom is the numerator degrees of freedom, this, and the denominator degrees of freedom. We put mean square error in the denominator, so degrees of freedom error we use in this case. So that's gonna give us this value, 8.44 times 10 to the power minus 5. So it's almost looking like a zero. It's so small. Let's repeat the procedure for calculating the p value for b. Statistical f dist rt. For x, you're going to put the f value. For degrees of freedom 1, you put degrees of freedom for factor b. For degrees of freedom 2, you put degrees of freedom for error. And again, very small p value. And let's do it for the one last time. Statistical f dist rt, interact f value for the interaction effect, then degrees of freedom for interaction, and degrees of freedom for error. Okay, so what we will do is let's clean a little bit. Let's make this up to only two decimal places. So format cells, number, two decimal places. So that's good. And let's make the p value up to four decimal places. Okay, so here we are, and now we write our conclusion here. So if our p-value is less than alpha value of 0.05, that means that factor is significant. Okay, so yes, p-value here is less than 0.05. So conclusion is factor A has a significant effect on the yield, the response variable. So significant, factor A is significant. What about factor B? We have to compare this p-value with alpha value of 0.005, 0.05, right? 5%, 0.05. Once again, this p-value is smaller than alpha value. So factor B also has a significant impact on the output. Not as significant as A, but it is still statistically significant. And what about interaction effect? Well, it is the p-value is higher than zero point zero 0.05 value of alpha. So that means the effect of AB with a low, very low F score with a p-value that is greater than zero point zero 0.05, we can safely say that interaction has no effect or insignificant. Interaction effect is significant. Insignificant, right? So that's our final conclusion. Now what we can do next is, now that we know that only the main effects of these factors, main factor effects are important in the chemical reaction, and interaction effect is insignificant, we can remove this term from our statistical model and we can refine our model that will only consist of two terms, factor A and factor B. And we can, uh, when we do that, when we remove this AB and combine it with experimental error, what will happen is our experimental error degrees of freedom will go up from 8 to 9, and our statistical model will have only two factors. So that's it for this video. We have taken the simplest case in 2 raised to k factorial designs, which is basically 2 raised to 2, two factors each at two levels. We have we have discussed a problem. We discussed the theory of that, and then we uh, actually solve the problem using Excel. So we now with this, you should be able to solve any problems at least for 2 raised to 2 case. So the video is getting longer. I will stop here. Thank you.